Hello, I'm Robert Toomey, and this presentation is a quick technical update covering my experiments with using JSON and shared memory to wrap Python using the RAPIO C++ library. RAPIO stands for Real-Time Algorithm Parameter and Input-Output. The name is the primary focus of the library. First, let's give a little background. Python has many advantages. You'll find that in many research institutions, including NSSL, scientists love the convenience of programming in Python. They can install various versions and libraries for their own purposes and have custom installs set up the way the individual wants or prefers to use it. In general, an interpreted language like Python can be a little easier to work with out of the box. Those from non-computer science backgrounds tend to find an interpreted language easier to learn and to use. It can actually be a little faster to code in, since when you change some formula or math in your code, you don't have to wait on a possibly long compile time to retest your changes. All of these features can be very convenient for the researcher who is probably just wanting to get everything to work however they can and possibly get a paper out of the door. Python libraries dealing with graphing, charts, statistics, etc. are all out there and fairly simple to install and use. Okay, so now let's talk about the disadvantages of Python. Like I said before, scientists install their own versions and libraries, usually custom to what the researcher wants. One of the first issues with this that we run into in DevOps is system installs versus bleeding edge. For example, we may have a requirement to run in a CentOS 7 system that comes stock with Python 2.6, while the researcher has installed the latest standard Conjura Python build. It becomes very difficult to synchronize a standard operational build without running into conflicts with setups of individual users. Another issue is that Python is a bit slower. It's less of an issue over time as hardware improves. However, since our stuff runs mostly in real time where we are constantly pushing the envelope of what we are doing, this does have a negative impact and is something to take into consideration. The main issue, though, is API. If I want to read netcdf, why not just use a Python library somewhere and hack out my own reader and writer of custom formats? The problem is that this leads to drifting APIs as people reinvent the wheel. If we change the C++ version of the netcdf reader to include new attributes or data, now anyone who's made their own has a broken reader. So basically, in general, this style of installing works well for individuals, but it doesn't work well once you extend or migrate that code into a large interconnected real-time algorithm system. So let's talk about two Python C++ solutions. The first is to completely write out all data files and messages in C++ and then reread them completely using Python. The advantage of this method is that you're completely decoupled. The Python handles its own reading and writing. It doesn't care about the system as a whole. The disadvantage to this method is extra and possibly unnecessary disk I/O. It also has the API drifting problem we mentioned earlier. You've got to keep all your reader writers that deal with data and notification messages in synchronization with your C++ API or everything breaks. The second solution is to actually compile against Python development headers and use a native interface to send serialized objects to Python code. This solution is also used in other languages such as C++, Java using the Java native interface. The advantage is probably the best possible speed with a true native interface. The disadvantage is having to link against some form of the Python source code and Python development libraries. This turns into a nightmare when dealing with multiple Python versions on the system. Also, in general, actually using native interfaces tends to have a fairly complicated API, which confuses non-computer science researchers and adds dependencies that don't make much sense to them. Finally, you're locked to the native language here in your implementation, only allowing calling a Python script, not a Perl or say a PHP one if you wanted. Why lock yourself to only being able to call one particular scripting language? So with RAPIO, we're trying something in between the two other solutions. Remember, RAPIO's main goal is to act as a C++ wrapper where it hides input, output, and notification of data from the algorithm writer as much as possible. Therefore, to accomplish this, RAPIO wants to just let the Python deal directly with the data itself and not have to reinvent the wheel to work with this data or notify about it. RAPIO uses the Boost C++ shared memory model and the Python shared memory model to read and write shared memory using Linux's dev.shm memory space to communicate between the two processes, kind of like when you're like a REST interface querying a web server. The design breaks data down into two distinct types. The first is the attributes, or typically metadata, which can be represented using pure JSON. The second is currently data arrays. Almost all of our data is represented in arrays of floats, integers, etc. These can map directly to standard Python NumPy arrays. So pictures are always worth more than words. So the next few slides will give a clearer idea of what RAPIO is actually doing. This graph shows the current design where RAPIO handles data and notification from various providers. You can see on the top left various data formats in the form of netcdf, grib2, XML, and JSON. These formats are read in and written by RAPIO. However, in a real-time archive system, we also need to know what files to actually look for, and we need to notify when new files are written. For example, in Woods 2, we have XML records called FML that notify of an available new netcdf file to read. This comes from a single file such as a codeindex.xml or some other XML sources such as watching a directory with Linux iNotify or polling a web server page. Now on the bottom left you can see these various notifiers. Now on the right side you can see RAPIO using dev.shm to communicate to other languages. RAPIO sends information out to the script uses it or modifies it, and it comes back to the C++. A couple more pictures will show how this is done and how to use it in Python. Here's an example of JSON generated by RAPIO that is sent to an external process. It's similar in nature to the attributes of a netcdf file, along with having extra information describing arrays and dimensions of the provided data in shared memory. It's RAPIO's JSON format, however, so the API will be able to get or retrieve back whatever information we want from this. Here is also a quick look at the internals of RAPIO doing its thing with the Boost C++ shared memory library. These pictures are more for developers to get an idea of how we are implementing it. As an end user of the library, you'd probably be more interested in just it working conveniently for what you're wanting to do. So with that in mind, let's now just look at a Python script that you would create to be called by RAPIO. This is how it currently looks and works. Though if it is embraced and used, the interface will probably expand and grow. This Python code here would accept any 2D data grid from RAPIO. In other words, right now we can send a lat long grid, a radial set, or a 2D single grib2 data field from an incoming file and use that data or modify it. Basically what we do here in the last few lines, if you look at the bottom, is that we set two cells of the data to contain values, and that's all we do. I just realized that we should check the bounds, but you get the idea. However, the thing to note here is that now the netcdf output of the lat long grid netcdf file is modified with these values. You're modifying the main output of the C++ of RAPIO. Of course, you don't have to modify it. Another usage case here would be to just take the input data and graph it or use any Python library you want to process it with. We've simplified it down to dealing directly with a prepared NumPy array and taking almost all the work out of your hands. Also, your script isn't going to break horribly when the formats change. RAPIO will take care of that internally. So let's look at the action list involving this. We can expand upon the Python library module over time. Currently, reading and modifying data in place are allowed, but not creation of new data directly in Python. You can get around this currently by having the C++ wrapper create your new data space in advance for you. Also, right now the JSON is static, and maybe allowing the JSON to be modified could be nice, but that would be a lot of work, I think, for that. We probably cover about 80% of the use cases already right now. Also, we're not passing in 3D data yet, such as lat long height grids, but we should just have to type up those functions for it, and it should work the same. Since this method uses shared memory, there's nothing stopping you from running an interface module in the language of your choice. In other words, we could probably have a module library for any language of interest. The goal, of course, should always be keeping the script language calls as simple as possible to allow researchers to quickly do what they need to do and waste less time trying to reinvent the wheel. So anyway, where's the code? Currently the code is at GitHub at the following address, http://github.com/retumi/rapio. Once again, thanks for watching and have a great day.